I'm Manu Drivers from Definity, and this talk is about replica resumption, which means that the machines powering the internet computer can always catch up to the latest state. Before we go into the details of that, let's look at the bigger picture and see why we need this. We're trying to build the internet computer that allows nodes in data centers across the world to collaborate via the internet computer protocol, thereby forming this virtual internet computer which provides a secure and reliable way to run software canisters. To make the internet computer scalable, we have the concept of subnets, where groups of canisters run together. We can increase the capacity of the internet computer by adding subnets. Within each subnet, we want to make sure that canisters run securely and reliably. Securely meaning that the state of the canister only changes according to the rules of the canisters, it cannot be tampered with, and reliably meaning that canisters in the subnet do not suddenly stop running. We do that via an approach called replication. If we look under the hood of a subnet, we see that it's powered by multiple replicas. This is a process that we call replication. Each of the replicas holds all the states of the canisters and processes all the messages that should be processed by the canisters. Now what we want to make sure is that even if some of those replicas powering the subnet, even if some of them are offline or even malicious, the subnet continues to make progress and process messages for the canisters. More precisely, as long as less than a third of those replicas are offline or malicious, so more than 2/3 of them are online, available, and participating in the protocol, then the subnet continues making progress. For this replication, we use a consensus protocol such that all the replicas process the same messages. And more precisely, we do that via a blockchain. So each of the replicas on the subnet has its own view of the blockchain, and they try to exchange artifacts via a gossip network. Now, of course, we know that sometimes some of the replicas might be unavailable. Perhaps replica 4 is temporarily disconnected from the internet. Now we want the protocol to work in a way that it's fault tolerant. The remaining 3 replicas on the subnet should be able to make progress even if replica 4 is offline. If another replica would now be unavailable, then the subnet would be stuck because more than a third of the replicas are offline. If replica 4 now comes back online, it's able to resume to fully catch up to the latest state of the protocol. And now, because we have more than 2/3 of the nodes being available, the blockchain should grow again and our subnet continues processing messages. Additionally, we might at some point want to add a node to a subnet, perhaps to increase the fault tolerance on the subnet. But this node comes in without knowing anything about the state of the subnet. Here, again, we need the node to be able to fully catch up to the latest state of the subnet such that it can participate in the protocol. Okay, so to recap, we want that whenever more than 2/3 of the nodes of a subnet are online and available, the subnet must grow such that the canisters on the subnet run in a very reliable way, even if some of the nodes powering the subnet are offline or malicious. And a result of this is that an honest replica must always be able to catch up to the latest state, no matter how far behind it is. And sometimes this is actually very simple. Suppose replica 1 has a blockchain up to height 29, but replica 2 is a little bit behind. Now, whenever replica 2 has a good connection to replica 1, it can simply obtain the missing artifacts and get a complete blockchain such that it's fully up to date. This is very simple. However, there's one complication. We want the internet computer to process many messages, such that the canisters can run very fast. But a downside of this is that all these messages must go through the blockchain, which leads to the blockchain growing very large very quickly. This means that replicas cannot store the blockchain forever. At some point, we have to delete the old artifacts to save space. And now imagine that replica 2 is so far behind that everybody else already deleted parts of the blockchain that replica 2 is still looking for. How will it now ever be able to resume and to catch up to the latest state of the protocol? That's the problem that we're going to solve in this talk. Another complication is that the members of a subnet can change over time. And since our protocol relies on verifying signatures from the members of a subnet, it's very difficult for a replica that's behind to know which signatures even to trust, because it doesn't know which nodes are currently powering the subnet. Luckily, we have a solution to this problem that we call chain key technology. Every subnet or every blockchain has one fixed public key. This public key does not change over time. The corresponding secret is actually shared between the participants of the subnet. And if the membership of the subnet changes, then the secret shares are securely redistributed over the new members. And the members of a subnet can now collaboratively sign an artifact on behalf of the subnet. Such artifacts can now be verified using this fixed subnet key. This will make it very easy to verify objects that were signed by the subnet, because all you need is one fixed public key that does not change over time. So even a replica that's very far behind and doesn't know the current members of the subnet could verify such a signature. So this brings us to our high-level approach to how we solve this resumption problem. We introduce a special artifact that we call the Catchup Package. This Catchup Package allows a replica to securely jump to a newer height, skipping parts of the blockchain. We sign this using this fixed subnet key, such that even replicas that are behind can always verify its authenticity and catch up to the latest state. And an honest replica makes sure it always has a catch-up package available and the subsequent blockchain. And together, they should allow other replicas to always fully catch up to the latest state of the protocol. The remaining question is, what exactly must go into this catch-up package such that a replica can securely skip ahead? To answer that, we'll first look into a little bit more of the details of the protocol. We use our blockchain to order the messages that should be executed on the subnet. And the result of that results in the replicated state of the subnet, which contains all the memory of the canisters. So using the previous replicated state and the messages in the block, every replica can compute the next replicated state. So for a replica to catch up, it needs to have one of these replicated states such that it can compute the next ones on its own. Additionally, blocks refer to this replicated state, and their validity is checked against some parts of this replicated state and the subsequent blocks in the blockchain. This allows us to ensure, for example, that one message does not appear multiple times in the blockchain and wouldn't be processed multiple times. To do such checks, the replica doesn't only need to have the right replicated state, but also needs to have some part of the blockchain. So this is another ingredient that likely needs to go into our catch-up package. Finally, we have the random beacon. The random beacon is also a chain, so we need to have the past random beacon to verify the next random beacon. The random beacon is also required to verify the consensus artifacts, because we use the random beacon to select the roles in the consensus protocol. So a replica will likely need to have a random beacon to fully catch up. So with this, we're ready to define our catch-up package. Replicas will regularly create a catch-up package. For example, every 200 heights. So once we reach height 200, replicas will check whether it's time to create a catch-up package. What they do is they see if they have a random beacon available, a block at that height, and the replicated state. And additionally, they check that the blockchain advanced to a point where older states than at height 200 are no longer required. If all of this is satisfied, then the replicas are ready to create a catch-up package for height 200. What they do is they group the replicated state, a block, and a random beacon together into a single artifact, which they sign with that special subnet public key. And now this artifact should be sufficient for other replicas to catch up. Note that the replicated state is actually too large to be included in the catch-up package, so we only include a hash of the replicated state, and the full state can be obtained via a separate state sync protocol that I won't go into today. Whenever the replicas succeed in creating such a catch-up package, they now can throw away all the older artifacts, because they know that replicas will be able to catch up even if they throw away these old artifacts. So let's see how replicas can resume from a catch-up package. So let's consider that we're a replica far behind the others, but luckily we obtain such a Catchup package over the network. Because it's signed in this special way under the subnet public key that we still know, we can verify the authenticity of this artifact and trust its contents. We now have a random beacon, a block, and a replicated state. And with that, we can, for example, follow the random beacon chain, because now we have a previous beacon to verify the next beacon against. We also have a block, so we can follow the subsequent blocks and verify the notarizations and the finalizations. And since we have a replicated state and the subsequent blocks, from that we can compute the next states. So the replica now has the latest blockchain and random beacon artifacts and the latest replicated states, so it's fully up to date and can participate in the protocol. So in summary, we want the internet computer to run canisters in a very reliable way, even if some of the machines that power the subnet are offline. More precisely, whenever more than 2/3 of the replicas on the subnet are honest and online, the subnet should make progress and the blockchain should grow. A result of that is that every honest replica must always be able to catch up to the latest state, no matter how far it is behind. At the same time, we know that the blockchain can grow very large, so replicas must delete all parts of the blockchain eventually. We have defined a special artifact called the Catchup package that is authenticated using the fixed subnet public key, and the Catchup package contains everything that a replica needs to securely skip parts of the blockchain and jump ahead to the recent state such that it can fully participate in the protocol.